ओके अभी हम लैप्लास ट्रांसफॉर्म के प्रॉपर्टी देखेंगे। लैप्लास ट्रांसफॉर्म के प्रॉपर्टीज और फूरियर के प्रॉपर्टीज मोस्टली दे आर सेम। मेनली कोई भी प्रॉपर्टी का यूज होता है कि वो प्रॉब्लम को मोर सिंप्लीफाई करना है। अगर कोई कॉम्प्लेक्स प्रॉब्लम है तो आपको बेसिक सिग्नल्स, देयर लैप्लास ट्रांसफॉर्म एंड देयर प्रॉपर्टीज आपको पता है, तो यू कैन फाइंड आउट लैप्लास ट्रांसफॉर्म ऑफ एनी कॉम्प्लेक्स सिग्नल। सो इट इज सो इजी। अभी तक हमने जो देखा है, और अगर ये प्रॉपर्टी आपको समझ में आ गया तो आप लैप्लास ट्रांसफॉर्म ऑफ एनी कॉम्प्लेक्स सिग्नल can be find out very easily. So same properties are there. First important property is the linearity, which indicates about the superposition theorem. So if two signals are added in the time domain, that is a a1 x1 of t plus a2 x2 of t, and its Laplace transform is a1 x1 of s plus a2 x2 of s. So this is the linearity property, which is a common, which the satisfy the homogeneity and the superposition principle. So accordingly you can find out separately and you can multiply by its weight, that is a a1 and the a2, and you can find out the Laplace transform of any combined signal is equal to Laplace transform addition of the combined signal. Then another important property is about the time shifting. If the signal is shifted in the time domain, that is x of t minus t0, if original signal, if we have for example, so e raised to minus at u of t, so this is a signal in the exponential signal in the time domain, this is t, and if this is x of t minus t0 means the signal is either shifted to the right hand side or shifted to the left hand side. If it is shifted by the t0 unit of the time, so this is t0, the signal will remain same. It is only shifted in the time domain. If the signal is shifted in the time domain, so its Laplace transform is going to remain same, only it is multiplied by the additional term e raised to minus s t0. Whatever value of t0 will be there, so this property is called as the time shifting property. Second important property is about the differentiation in the time domain. If the signal is differentiated in the time domain, that is d by dt of x of t, so its Laplace transform is equal to s into x of s minus x of 0 minus. So x of 0 minus is called as the initial value. Sometimes the initial value will be zeros. So d by dt of x of t is s into x of s. So similarly, if you take the nth order differentiation, so there will be s raised to n will be there. So accordingly you can find out Laplace transform of any differentiated signal. Then the time integration, Laplace transform of the time integration, that is minus infinity to t x of tau into d tau is equal to original Laplace transform divided by s, and its minus infinity to 0, that is the initial value, divided by s will be there. Then the frequency differentiation, if the signal is multiplied in the time domain by the t, that may be multiplied by minus t raised to n. So any order minus t raised to n, if n is equal to 1, it will be minus t x of t. If the signal is multiplied in the time domain by this minus t, so it's the Laplace transform is the nth order differentiation of the x of s. So accordingly you can find out Laplace transform of the x of t as a x of s, and whatever the it is multiplied by minus t raised to that n, so you can take the nth order differentiation in the s domain. Then this time shifting we have seen the frequency shifting property. So if the signal is multiplied in the time domain by e raised to minus or plus at into your the x of t, signal is multiplied by e raised to minus at, so then its frequency is shifted. So its Laplace transform is equal to x of s plus minus a. If it is minus, it will be plus. If it will be plus, it is a minus. So this property is called as the frequency shifting property. Next is a time scaling property. If the signal is scaled in the time domain, that is either compressed or the expanded in the time domain, so opposite operation will take place in the s domain. So if it is a compression in the time domain, it is expanded in the frequency domain because it is s by a. If it is expanded in the time domain, it is compressed in the frequency domain. So Laplace transform of x of at is equal to 1 upon mod a x of s by a. This is called as the time scaling property. Then the convolution property, if the signal is convolved in the time domain, so this is a convolution symbol. So if the signal is convolved in the time domain, so the Laplace transform is a multiplication in the Laplace domain. That is Laplace transform of x1 of t is x1 of s, Laplace transform of the x2 of t is x2 of s. So convolution in the time domain corresponds to multiplication in the s domain. Similarly, the multiplication in the time domain corresponds to convolution in the frequency domain. Again, two more very important properties in the Laplace transform are the initial value and the final value theorem. Basically, the initial value and the final value theorem are used to find out the initial value of the signal or the final value, that is at the time t is equal to infinity or at the time t is equal to 0. When you want to find out the value of the signal at the just time t is equal to 0, before that, so you can use initial value, and if you want to find out the value of the signal at the time t is equal to infinity, so that is called as the final value theorem. And the initial value theorem is given by x of 0 plus. 0 plus means value of the signal just after the time t is equal to 0. This is equal to, when it is a 0, then here the limit s tends to infinity you have to use. S is additional term, s into x of s. So initial value theorem, x of 0 plus is equal to limit s tends to infinity, s into x of s. Similarly, the final value theorem is given by x of infinity is equal to limit s tends to 0. Limit s tends to 0, s into x of s. X of infinity means value of the signal at the time t is equal to infinity. So limit s tends to 0, s into x of s. So both the case, s into x of s is there. Only here the limit will be different. For initial value, the limit will be s tends to infinity, and for final value, the limit s tends to 0. Now we are going to use all properties and Laplace transform of the basic signal to find out the Laplace transform of any complex signal.